Suppose we have a particle and this particle is somewhere in space. So in order to visualize this, it's always better to have a coordinate system. For simplicity, I'm going to consider here a two-dimensional coordinate system, and this is a Cartesian coordinate system with the coordinates x and y. So let's suppose we have a particle somewhere in the space, and this particle P, let's say its position at point P, having the coordinate values x, y. Then there are a couple of ways to represent this particle. So the most simplest one is we are going to use a position vector. A position vector is a vector which is always drawn from the origin, and it's a vector that's pointing away from the origin towards the point P, and we're going to represent this vector by R. This is the standard notation for denoting a position vector. So this is R vector. Then we have, at this point, we can also state the vector velocity. Now that's a very tricky part. So let's, for the sake of argument, we assume that this particle is moving along this trajectory. Let's say it started somewhere at point A and reached somewhere at point P, and had passed through point P. So at this point P, what we can do is we can draw a tangent line. When we draw the tangent line, so at that particular point, the tangent line is going to give us the direction of the velocity. That is going to tell us in the next moment of time where the particle is going to be. So that is the velocity vector. So let's say that this is the velocity vector. This velocity vector is defined as the slope of the tangent line, and the slope of the tangent line at point P is given by the rate of change of a position vector of the particle which is positioned at point P. So let's call it equation number 1. Now here we have assumed that vector R is equals to x times I cap plus y j cap. It has got two components, one along the x-axis and the other along the y-axis, with components value of x and y. Right. Now this particle, because this is in motion, we have only captured a particular moment in time, which is the point P. This particle has been moving, so that means it's going to have some kind of momentum. So the linear momentum and we are going to denote it by the symbol P, since it's a vector quantity, so it's a P vector. So the linear momentum of the particle is defined as the product of the mass of this particle. So this is not a massless or a point object. This particle at point P is going to have some kind of mass, and this is the mass denoted by m times the velocity at that point, or the velocity with which the particle is moving. So this is the linear momentum of the particle. So let's label it as equation number 2. Now, as the particle moves from point A to point B, there's going to be a lot of type of interactions with some external objects, and also there might be different kinds of fields that might exist here. There could be lots of fields that exist here, and this particular object is moving through this particular field. Also in this, as it moves through this space, it's also going to encounter some debris, let's say, some objects, different kinds of objects, different kinds of other particles it can collide with it. So there's always something happening here. So that means all these forces or which is acting on this particular particle, and also because of its being interacting with other particles on its way, so it's going to have different forces acting on it. So we're going to consider the sum total of all the forces that acts on this particular particle, and let's call it the force F vector. And this mechanics of this particle I mean, like how the way it moves, what kind of velocity it has, like where it's going to be, where it came from. All of this mechanics of this particular particle is contained in the most famous equation. Force is directly proportional to the rate of change of momentum. This is our Newton's second law of motion, which states that the force exerted on the particle at P is going to be directly proportional to the rate of change of momentum. Right? Now, this can be expressed as force is equals to some constant of proportionality K times rate of change of momentum. Experimentally, it is found that the value of the constant of proportionality K is equals to 1. So that means we have force is equals to rate of change of momentum. Now using equation number 2, where we have stated that the momentum is equals to mass times velocity. So that means we have the force vector given by rate of change of momentum will get replaced with its form, mass times velocity. Now we know that mass is a constant. So since it's a constant, we can pull it out of the derivative. So we have mass times rate of change of velocity. So this is our Newton's second law of motion, which is expressed as a first order differential equation given by m times rate of change of velocity. Now we know that the rate of change of velocity, dv over dt, is also known by another name, and that is referred to as the acceleration. Right? It's the acceleration of the particle. Right. So this is the Newton's law which we are most familiar with, just like F equals m times a, or F equals to ma. Now we're going to work with this particular equation. Here we see that there is like one more form in which this particular equation can be expressed. So let me write it down. This is Newton's second law expressed in the form of a first order differential equation. Now what we will do, we know that since dv over dt can be also represented as, so we have rate of change of velocity, and velocity is rate of change of position. This we have already mentioned in equation number 1. So this is the second derivative of r with respect to t. So that means our force equation can be now expressed as F is equals to m times second derivative of r with respect to t. So this is the Newton's second law expressed as a second order differential equation. So we have obtained 3 forms of Newton's second law of motion. So we have F equals to mass times acceleration. So let's say this is form number 1. In terms of us, acceleration can be also represented as the second derivative of the position vector r with respect to time t, and the first order differential equation, which is m times the rate of change of velocity. Now we're going to use this third form, and we're going to do a little bit of manipulation here. So we know that m times dv over dt can be also written as d v vector divided by d r vector multiplied to d r vector divided by dt. So this is the chain rule. Now this has been done so that we can replace dr vector over dt with the velocity vector. So this is v vector only. So we have m times v vector multiplied to d v vector divided by dr vector. So this is another, so we'll call it the fourth form This is not exactly a form. This is just a manipulation that will be used to solve an integral when we calculate the work done on a particle, and that is the next section. We will now understand the concept of work done. Let us suppose that our particle is moving from point 1 to point 2 due to some external forces acting on it, right? There could be different kind of external forces, gravitational forces or electromagnetic forces. We don't have to worry about it. We just say that some kind of external forces is acting on it, and because of which the particle is moving from point 1 to point 2. Now we can calculate the work done on this system, or we can say the work done on the particle by the external forces to move it from point 1 to point 2 is given by W12 equals to the integral going from position 1 to position 2 times F vector dot dr vector. So this is the formula for obtaining the work done on the particle. Now we are going to use the fancy form of force that we derived a couple of minutes ago. Force, so we found out that the force vector is equals to mv vector times dv vector over dr vector. So let's use this. So we have m times v vector times dv vector divided by dr vector dotted with dr vector. So m is a constant, so that can be pulled out of the integral. So we have m times 1 going to 2, then we have v vector dotted with dv vector. So v vector dotted with dv vector, it's simply 1 to 2 v dv cosine 0 degree, since v and dv are both in the same direction, and cosine of 0, so this is 1, so that means we have v integration of e dv, so that's simply half v squared with limits going from 1 to 2. That means the work done in moving the particle from point 1 to point 2 is simply given by m times half v2 squared minus half v1 squared, which is equals to half m v2 squared minus half m v1 squared. The scalar quantity mv squared over 2, this is known as the kinetic energy of a particle, and it is going to be denoted by T. So that means we have work done on the particle is given by simply T2 minus T1, the change in kinetic energy. Now, suppose that the work done is always the same regardless of the path taken. That means here we didn't consider that, we only assumed the final point and the initial point, and we calculated the work done in moving the particle from point 1 to point 2 because of the action of the external forces acting on it. Here we didn't consider what kind of path it took. Maybe it could have taken a straight path, or it could have taken any other path. It could have taken a very complicated path and then reached 2. It didn't matter. So in that particular case, then we say that the force and the system is conservative in nature. Only in that case, then whatever path it takes, then it's not going to affect the work done on the system. It's a work done on the particle that's only going to be equals to the change in the kinetic energy. Here we are assuming that there is like no other dissipative forces or frictional forces, and if those were present, then definitely this is not going to be a conservative force. That means it is going to be path dependent. However, in our case, we are only considering the situation when the force and the system is conservative. And in that case, our force field is going to be equal to the gradient of some scalar function. Let's call it phi. And the scalar function phi is position dependent. That means it's a function of the position vector r. Also, in this particular equation, f vector equals to the negative gradient of the scalar function phi appears whenever force is conservative in nature. Now, coming to the operator del. This is defined as partial with respect to xi cap plus partial with respect to y j cap plus partial with respect to z k cap. So this is the del operator. So if we have del phi, so that will be simply equals to partial of phi with respect to xi cap plus partial of phi with respect to y j cap plus partial of phi with respect to z times k cap. This scalar function phi has a name. The scalar function phi, which is a function of position r, is referred to as the potential or potential energy. It's referred to as potential or the potential energy. Now that we have the force expressed in terms of some scalar function, now the work done will be work done in moving the particle from 1 to 2 is equals to, so we have integration going from 1 to 2, force field times dotted with the dr vector. So in place of force we have negative gradient of phi dotted with the path dr vector, or simply taking out the negative. So del of phi is partial of phi with respect to x I cap plus partial of phi with respect to y j cap plus partial of phi with respect to z k cap multiplied to dr vector. So we had r vector given by x I cap plus y j cap plus z k cap. So the differential dr vector will be simply dx I cap plus dy j cap plus dz k cap. So let's dot it with this particular value. That means we have dx I cap plus dy j cap plus dz k cap. Now we take the dot product. So the dot product should give us negative integral going from 1 to 2. So we have partial of phi with respect to x times dx plus partial of phi with respect to y times dy plus partial of phi with respect to z times dz. Now this is a definition from the differentials. This is simply d of phi. That means integration of d phi will be phi with limits going from 1 to 2, and this is phi 1 minus phi 2. So this is the work done in moving the particle from 1 to 2 in a conservative system. Now earlier we obtained that the work done is defined as the change in kinetic energy T2 minus T1. So we can say that T2 minus T1 is equals to phi 1 minus phi 2. And rearranging this equation, we can say that T1 plus phi 1 is equals to T2 plus phi 2. This means that if the forces acting on a particle are conservative, then the total energy of the particle T plus phi will be conserved, where phi is the potential or the potential energy. Now we're going to talk about inertial frames of reference. So let us begin by assuming a coordinate frame. So let's start with a coordinate frame. This is a Cartesian coordinate system. We're going to consider x1, x prime, y prime, z prime. That means here we're considering a coordinate frame s prime having the origin O prime, and we're going to measure the position of a particle, say P, with respect to the origin. Let's call it, that's denoted by the position vector R prime. Now we have another frame of reference, and let's call this frame of reference S, which has an origin of O. With reference to origin O, we will also find out the position vector of the point P with respect to frame S. So let us construct a vector going from point O to point P, and this is represented by R vector, which is the position vector. Then, based on this idea, we can also find the position of frame of reference S with respect to S prime. So let's call it R vector. Now, here we have a triangle. Now, using the triangular law of vector addition, we can say here R prime vector, that's equals to R vector plus small r vector. Right? Now we're going to take the derivative on both sides with respect to time t. So we have d r prime vector over dt is equals to dr vector over dt plus dr vector over dt. So capital R vector, so this R vector represents the position of frame of reference S with respect to O prime. Now suppose that this is moving. This frame of reference S, this is moving with a velocity of v. So that means this is the velocity v. So we can say that velocity v vector is simply dr vector over dt. So we can write our equation as d r prime vector over dt is equals to v vector plus dr vector over dt. Let's again take the derivative on both sides with respect to t. Then we have d squared r prime vector divided by dt squared equals to dv vector over dt plus d squared r vector over dt squared. Now we consider that the particle has a mass of m, so that means we're going to multiply this equation throughout by m, so that should give us m times second derivative of r vector prime over dt squared equals to m times dv vector over dt plus m times d squared r vector over dt squared. This is simply the force on the particle at point P measured with respect to the frame S prime, which can be written as F, the force, which is a function of R prime. This is equals to m times dv vector over dt plus the second term md square r vector over dt square. So this is the force on the particle at point P measured with respect to frame S. So that means this is a function of r vector. Now, if we suppose that the velocity v is constant, that means our frame of reference, that is frame S, let's consider frame S prime to be fixed, and frame S moves away from S prime with a fixed velocity v, then the rate of change of velocity with respect to time will be equals to 0, and in that case our formula will become the force experienced by the particle measured with respect to the origin of S prime will be equals to the force experienced by the particle at point P measured with respect to origin O of frame S. Now if V were not constant, I mean this term will be always present, and we can say that we have a non-inertial frame of reference. So this is the case of a inertial reference frame.